Okay, good morning. It's my pleasure to be here. Thanks for having me. And so today I'll talk about a topic that I'm actually very excited about, which is dealing with rare data in computer vision. I've worked on this starting from my PhD, and I'm still continuing with similar topic. So why is it that I like this problem? Well, it turns out that actually the world behaves like that. It's just for some reason it gives us more data for some concepts are very popular. But for other concepts, we have only a few data, or it's very hard to collect data, right? So for example, if you consider the Sun 397 data set, so, and then plot the histogram of the instances that you have in that data set, you'll see that the living room actually is the concept that has the most instances to actually work with. But when you actually find a skateboard park, the number of instances that you have available is actually very, you only have a few instances to work with. To give you another instance of this problem, feature matching is another good example of this. So when you actually match features from two images, many of the candidate correspondences that you get are actually wrong. So only a few portion of them are actually good. Okay, so in nature, these true correspondences are actually rare. Okay, and well, we actually have to learn how to deal with these rare events. For example, consider a self-driving car, right? Many of those systems, or the perception systems that they have, very likely they have, or they're trained with the common scenes or common events of the world, right? But consider the case, I don't know, that this self-driving car is actually seeing this baby crawling on the street. It is a very unlikely event, but actually do happen. Actually, when I was creating this slide, I found a few posts in the news where actually this happened. So if we don't learn how to deal with these rare events, we can have horrible outcomes, right? So I organized the talk as follows. So first, I'm going to talk about what I did essentially in my PhD, dealing with correspondences and treat them as rare events. And then I will switch to current topics that I'm actually working on right now. So the second one is learning directly from a long-tailed data set. And then the third one is mainly just a visualization framework for CNNs dealing with pixel-level tasks. But it has a relationship with rare events, especially I was interested in seeing how CNNs behave for input that the CNN has never seen before. And then I'll just conclude, okay? So I'm going to start with correspondences and feature matching. And this work essentially aims to improve Runsack-based algorithms to make them faster, but with a novel insight of treating these correspondences, true correspondences, as rare events. And I'm going to be using statistics in order to model those rare events in order to do so. This was joint work with other collaborators, Sergio Rodriguez, Pradeep Sen, and Matthew Churk, of course. So image correspondence, or solving this image correspondence problem, is actually fundamental in computer vision, right? So thanks to the solution for that problem, we can actually reconstruct large 3D models. We can actually localize cameras if we have a 3D model, for example, or we can do image stitching and many other applications. So it's an important problem. As I mentioned before, solving the image correspondence problem typically throws us data that is not useful. Okay, so when you actually get the candidate correspondences, I will say that actually 70% of them are actually wrong. And so if we're lucky, 30% are actually good. Okay, and this is caused because of many things like rotation, illumination, scale variations, and the poses of the camera. So those factors actually affect the feature matcher. So basically confuse it. Okay. Now, so the goal here, or one of the first goals when I started my PhD, was, can I actually predict which of those candidate correspondences is true, or is a good one, based on the similarity scores that I get when I run the feature matcher, okay? And to give you the solution that I came up with, first let me review actually how is it that the feature matcher works. So imagine that I give you these two images. I want to reconstruct, say, for example, the Colosseum. So the first step that you do is that you detect your features, which are visualized with these circles. And then you basically forget about the context of the image, where that feature was located for now. And then what you do is that you only graph patches surrounding that feature, okay? Then the next step is that you say, for example, that you want to find the feature matches for this query feature. What you will do is that you will compare a representation, say, for example, sift or surf, against all your reference features that you have in your database. So basically, this nearest neighbor rule, right? So you will actually have to compute, say, a distance between their sift descriptors. So you collect them. And then what you do is that you basically grab the minimum and select or establish that correspondence following this rule, right? So essentially, it's just selecting the most similar feature based on some appearance representation. So these scores are going to be my random variable of interest, okay? I want to predict, based on this data, if the correspondence is actually true or false. So this is actually the statistical model that I came up with. And the main idea is as follows. So if I have a minimum distance for a true correspondence, somehow that minimum distance should be an outlier with respect to the distances of the false matches, okay? So if we have a good representation, which in this case SIFT is actually a good one, it has proven to be a good one, then very likely that score should look like an outlier with respect to the statistics of the false matches. Okay, so overall, you can actually think about that there's an underlying process with two distributions. One distribution that is essentially drawing distances for good correspondences, and another distribution that is giving you samples for false matches. Okay, so when you collect these distances, essentially when you run your feature matcher and you collect this set, so it is equivalent, or you can think about getting that data set as drawing from this mixture model, right, from these distributions. Now, since I'm actually considering a 3D vision problem, at most I can have a correct correspondence, right? That's because feature matching aims at identifying the same 3D point depicted at two images, okay? So at most I can have one good solution. So this means that this set, if I'm lucky and I have a correct correspondence, I'm actually drawing one sample from this green curve, which is representing, in this case, the true correspondences. But then I actually have a lot of false matching scores, right? Because there are other points, and therefore I'm going to get scores that are actually coming from this red distribution. So the goal here is that somehow what I want to do is model the scores coming from this distribution, because I actually have more data for it. Right. For example, if you want to fit a parametric model, you know that you need a lot of samples to actually get a good estimate of the parameters that you want, right? But in this case, if I were to fit some model and try to get some parameters, I only have at most one sample. So it's not going to be that reliable from one sample. Whereas in this case, from the false matches, it's rich in data, right, as I explained before. So I can actually work with this. Now, rather than actually working with all the, oh, you have a question?
So is this distribution for a single Y, or in fact you pull all the Y's together?
This is considered only one feature, one query. Okay. So imagine that I have one query feature, and then I just compare that query with all the rest. So this is only for one. Okay. Okay. So rather than actually using the entire data that I have here to try to come up or estimate a distribution, parameters of a distribution, what I'm going to do is actually try to focus on the minimum distance that this process can actually generate. And that's because the nearest neighbor matcher, it only focuses on the minimum distance, right? So the rule is telling it to only decide based on the minimum distance that you get out of this sampling. So the goal is then to model what is the minimum distance that this process can generate. And for that, there are statistical theories that give you the distribution that models that behavior. So once I have that model of the minimum distance coming from this red process, then I can actually do a test and check if the minimum distance that I have agrees with that model that I just computed. If so, then I can actually predict that it's false. Otherwise, it's actually good. That's the whole idea of this approach.
Do you expect the false correspondence matches to also follow a single P Gaussian model?
Oh, that's actually a good question. So this is just an illustration. I'm not assuming a Gaussian or anything like that. This is just to illustrate that I have two distributions. They may have weird shapes and so forth. This is just to illustrate that I'm considering two processes here. Yep. So, okay, so what I'm going to use here is something that is called extreme value theory. And it's a statistical theory that deals with maximum or minimum of a random process. Essentially, it aims to give you the distributions that will model either the largest scores coming from a random process or the minimum scores from a random process. And in particular for this problem, the theorem that works the best is something that is called the block maximum theorem. It turns out that in the limit you can prove that the distribution that models the minimum or the maximum is a distribution called the generalized extreme value distribution. So it is actually a very complex distribution, but it is so general that in the limit it actually holds. And according to the theory, it holds for a lot of processes. And it has special cases. So one of the special cases that I've been using a lot is actually the Rayleigh distribution, but others that are common, for example, are Weibull, Freckett, and Gumbel. Okay? So just to give you an example of how this theory works, imagine that I have a normal distribution in 1D. Okay? And then imagine this experiment. So I'm going to draw 10,000 samples from a Gaussian, from this Gaussian distribution, and then you keep the minimum of that. Okay? Then you draw another 10,000 samples from the same distribution, and you keep again the minimum of that. So you repeat that process or that experiment multiple times, saving the minimum score that you got. Okay? The distribution that is going to model those minimums is actually the GEV, or the generalized extreme value distribution, according to this theory. So what I'm showing here is that I actually ran that experiment. So I drew these samples, and I fitted the GEV. So this will be the GEV, the distribution modeling only the minimum samples that this Gaussian distribution generates. Okay? Does that make sense? And just to give you a bit of an evidence that this actually works, this is a sum of this, but it's actually plotting the histogram of those minimums that I stored when I was running this experiment. So this is a very general way to model minimums and maximums. I mean, it should be easy to see that maximums can be modeled as well, because you can turn a maximum by just negating that score, right? So you flip. It's like in an optimization.
So for a Gaussian distribution, what is the theoretical limit?
The theoretical limit?
For that distribution of minimum.
So are you asking like if you're drawing from a Gaussian distribution
and you're actually plotting the distribution of the minima, right? So is there a theory? What should the right distribution should be?
The right distribution is this one, the generalized extreme value distribution. But are you asking about the bounds? Like what would be the?
Is it parametric?
Yes, this is parametric model, but it's unbounded. I mean, this model comes here, okay? But it's actually very unlikely. So what this is saying is that most of the time when you take the minimum from a process, very likely it's going to fall in this region.
Right.
It's not telling you.
Is there like an equation that you can write?
Yes, there's a parametric form for it. Yes, it's part of an exponential family, so it has scale, shape, and location. Okay, so it's actually parametric. Yeah.
And is the fitting the curve you shown on the right is the fit you have made on the observed data?
Yes. Okay. Yes. So this histogram is the histogram of the minimums that I kept, and then the red curve that you see is the GEV that I fitted. So I'm going to use this model for modeling the minimum scores of the false matches. Okay? And then I'm going to use this to check if the minimum that the nearest neighbor matcher is using to decide agrees with it or not. Okay? So the algorithm is pretty simple. So what we're going to, before I move on here, I forgot another thing. In order for this to work, we actually have to grab a large number of samples, right? So imagine that instead of grabbing 10,000 samples, I only grab 2. So the likelihood of, the domain of where of those samples will be, very likely is going to be around 6, right? So if you only grab 2 samples, very likely you will get a common, or what is considered a normal value. But when you grab a bunch of them, then your chances of getting rare data from the process increases. So this theory essentially requires a lot of data to make sure that you have rare cases so that you can actually fit this distribution. Okay. Okay, so back to the problem. So this is the algorithm. It's actually fairly simple. So once you actually computed all the distances comparing all these descriptors, the idea is then to only focus on those that are small, right? Because I'm deciding based on the minimum distance. So in this case, I'm just going to grab k smallest distance. And then the idea is to fit an extreme value model based on the theorem that I showed earlier. But in this case, I'm going to discard the minimum distance. And that's because if it turned out to be correct, then the model will have a bias implicit in the fitting, right? And I don't want that. But very likely, the remaining points will come from the false matching random process, right? That's because I have a lot of data from it. So then this estimate is going to be fairly OK. Then once I have my distribution that I call G, in this case, by the way, I'm using capital letters for CDFs. And what I'm going to do is use the CDF to check the minimum distance or the agreement with it. So my minimum distance that I kept, I'm going to evaluate the CDF there. And then I'm going to have another threshold that's going to help me decide. So if this value, which is some probability, is actually above this threshold, then I can actually predict that it's a false correspondence because it's agreeing with the model of the minimum distance. If not, then likely I can predict that it's a good one.
I'm kind of curious. Can you go back to the previous slide?
Yeah.
Suppose you say you need a lot of samples
Yeah.
to compute that.
Yes.
Suppose theoretically, right?
Uh-huh.
Your sample is close to infinite, which
Okay.
means that your minimum is actually very, very, very small.
Yes. Yes.
So that means that the more samples that you take, the more to the left the red curve is going to be, right?
Yeah. Yeah. But you know, in practice, I mean, that's
Well, yeah, I'm just
yeah,
talking
yeah.
about theory.
yeah. Theoretically speaking, you can prove in the limit that actually it'll converge of something like this. What you're talking about is the location of this distribution. Yes. Yes. So yeah, the sample will affect the location of this distribution. Yeah, for sure. But in the limit, it actually is the parametric form that describes that.
But you know, this web can go to select slides.
To this one?
This is running per query, right?
Yes, per query. That's exactly right. So here it's fine because typically when you detect features, you will get like 1,000 features or 2,000 features. Of course, depending on the scene that you're seeing, right? If it's well textured, you will have a lot of features. But if it's a wall that with no texture at all, probably you will have a few. But yeah, this is run per every feature, yes. OK, so this is the algorithm. It's fairly simple. And so the distribution, the generalized extreme value distribution has some parameters that are actually hard to fit. And actually, it turns out that the maximum likelihood estimator has some nice properties only under certain conditions. But then if you don't comply with it, then there's no guarantee of maximum likelihood at all. So in order to avoid any issues with it, so we decided to use a special case of that, which is the Rayleigh distribution. It only has one parameter, which is the scale. And that'll sort of like minimize those issues that I was explaining. So I'm going to show you some experiments that I did and some results. So for this experiment, I used the dataset that is widely used in the community. It is called the Oxford Affine Covariant Datasets. It's giving you basically a bunch of images. And for every image, you have homographies. Remember that homography is transformation from pixel to pixel, from image 1 to image 2. So they give you this ground truth. Okay, so you can actually get or determine what are the right correspondences when you do this experiment, thanks to this homography. So you can actually run your matching method, and then thanks to the ground truth, you identify which correspondences are good. So these are actually ROC plots. You know, true positives on the y-axis, meaning that how good my predictor worked, you know, determining the right correspondences. On the x-axis, we have false positive rate, which is meaning the rate of false alarms, meaning that if the classifier thought it was correct, but in reality it was not. Okay, so clearly what we want is a point that is high in true positive rate and minimum in false positive rates. Okay. So in order to get this curve, you vary the threshold. So I don't know, from 0 to maybe some high number. And that's how for every threshold that you have a point in this curve. Okay, so I'm actually evaluating several thresholds at the same time. So these are a couple of baselines that I'm comparing the proposed approach. The proposed approach is actually the red curve. We named this meta recognition Rayleigh. So on the left we have for SIFT features, and on the right we have for source features. The main baseline here is what I call lowest ratio, but also in the community it is known as the SIFT ratio test. That test is very simple. So when you do your matching, you get your distances. You divide the smallest distance and the second smallest distance. That ratio is widely used in the community to actually filter bad correspondences. Then I used another baseline just to compare something that is called the Brown's ratio. It was paper CVPR. It's very similar to the SIFT ratio test, but instead of dividing the smallest distance with respect to the second one, we take the average of the second one and the third as the denominator, and then we again compute the ratio. So that is the black curve. And then there's another method that is very similar to the one proposed, but it was proposed mainly for visual classification. And what they found in a PAMI paper is that the Weibull distribution, at least for those problems, worked well in another domain. So here I'm showing that the Rayleigh distribution for feature matching actually works well. So as you can see here, the red curve is above the other methods, which means that this seems to be working okay. So on average, you will see an improvement of 3 to 5%. Okay? If you just want to predict true correspondences by just using the similarity score of the SIFT matches. Okay, so this turned out to be really good. And then the next problem that I wanted to tackle, given this, was to speed up all the estimations that occur, for example, in structure from motion, right? So once you have these correspondences, you, at the end of the day, want to get a 3D model or maybe estimate a homography or fundamental matrix in order to do other things, to understand, for example, the relative motion of cameras and so forth. And in order to do that, we actually have to run something that is called Runsack. And Runsack can be slow, especially if we pass an image pair that has only a few correspondences that are correct, say, for example, 5% or 1%. It's going to take forever. So just to remind you about Runsack, Runsack is this iterative algorithm where you have your candidate correspondences in our domain, but it's actually more general. You select randomly a subset of the data. Then based on that subset, you fit a model. Basically, you get a hypothesis. And then the next step is to check with the data itself and say, OK, how many points in my data set agree with the model that this hypothesis that I just drew? Okay, so you repeat this, and you always keep, it's sort of like a greedy algorithm. You always keep the one that is explaining the most of your data of the candidate correspondences. And then once you reach a number of iterations, you return the best model. So I wanted to speed that up. And one way to do so is, well, Runsack originally is randomly drawing points from your data set using a uniform distribution. So every point actually is equal, right? But given this previous knowledge of this predictor, right, I can actually get a score or indicating which correspondences are likely to be good. So this CDF that I was evaluating with the minimum distance can be used as an informative feature, right? I can actually normalize that and get a distribution over the correspondences and get some sort of an important sampling strategy to do so. So if I follow that sampling strategy, then very likely I can speed things up, because very likely I will hit the correct correspondences and get the models very quickly. So that is the idea. Now, if we use the scores from the previous algorithm, it actually works well. But I actually found out another way to speed this a little bit more.
Yeah, but the position of the distribution is depending on the number of sampling, right?
Yeah, that's what he was saying. Yeah, so depending on the, yeah.
In your case, is there any relation between position of the distribution and the sampling, you need that knowledge, right? In order to apply the threshold or whatever.
Yes. Yeah.
In
So.
this Runsack case, you need. Let's suppose you have 10,000, correspondence about whatever. Then you can predict where the distribution is. Is that right?
In theory, I could. Yes.
Then how you can apply the that yourself?
I'm not.
The reason is in order to determine the threshold position. You have to know the distribution position. Right?
Yes.
And that distribution position is related to the number of sampling, right?
Yes, it could. Yeah.
Could.
Yeah.
Then how to determine the threshold value?
Okay, so the way I did it in my experiments is that I got a training set offline and I computed the threshold there. And then I used it in a testing set.
Oh, I get it.
Yeah. But yeah, in theory, yeah, I will have to do, that will be a problem as you described, yeah. But luckily in practice we can actually do this. All right, so just to continue, I wanted to follow a different strategy, very similar to what I showed earlier. But as Gang actually was mentioning, the algorithm that I presented is actually for every feature, right? So I have to compute that for every feature. Well, I can actually grab the entire information from all the features and exploit it, right? So essentially, if you have these query features and then you compare with your reference features, you can actually create this matrix where you arrange the distances such that for this row, where the rows are actually corresponding to the query features, and then the columns are giving you or storing the distances that you get when you compare, say, for example, this query with all the database or reference features over there. So every column essentially is a comparison, okay? And so every row corresponds to the query features. Now, the predictor that I showed earlier was working only with one row, okay? But I can actually exploit all this data and then probably do something better in order to gain more data, right? And feed up another model. So just remember that the random variable of interest is actually the minimum distance always. So we're going to be focusing on the minimum distance of every single row. What I want to do here, or the idea, is actually to come up with a mixture model that describes the statistics of the minimum distance when I run the entire matcher, considering all the information that I have, okay? I still have a lot of data coming from the false correspondences, so I should be able to use EVT no problem. But for the true ones, probably I won't have enough. It depends on the images. So I cannot use EVT directly. So for that, I will have to do something else that I'll explain in a second. So what I came up with is, again, another very simple approach where I'm going to assume a mixture model of this sort. And this F is a CDF modeling all the minimum distance that I've observed when I matched my features. It could be good or bad, okay? But similar to the previous algorithm, I'm also considering two processes. One that is explaining the correct distances explaining the distances for the correct correspondences, and another one for the bad ones. So you know that in a mixture model, you need a mixture parameter, right? In this case, that mixture parameter is called the inlier ratio. That inlier ratio essentially is the probability that if you select a random one candidate correspondence, what is the probability that that one will be a good one, okay? And so the mixture model is actually fairly simple. So you will have two densities that are mixed together thanks to this inlier ratio. So these are actually, these models, the CDF. For the false matches, again, I'm going to use the GEV because I have a lot of data and I'm focusing on minimum, so therefore I can actually use EVT. But for the ones that are actually correct, I may not have enough data and I may not be able to model it with a GEV. So here we actually had to look into the histograms and we determined that the gamma distribution was modeling well the shape. So here we just use gamma. And so now the importance of a correspondence to do this sampling for Runsack can be simply calculated with a Bayesian approach, right? So if you do your Bayesian math, you will use the PDFs and you will get a function that if you pass the minimum distance in question, it'll give you a likelihood that that one is actually going to be a good match or not. So this is what I'm going to be using for speeding up Runsack. Now the problem is that now I actually have to recover all the parameters for each of these distributions and the inlier ratio from the data. Okay? So in order to get those parameters, I propose the following algorithm. So the first step is going to be using the predictor that I introduced earlier and separate those minimum distances that are likely to be good and likely to be false. Then for those that are labeled as good, I'm going to feed a gamma distribution. And then for those that are labeled as false, I'm going to feed the GEV distribution. And then the last parameter that I need to estimate is actually the inlier ratio. For that, I propose solving the following least squares problem. Okay, so let me explain how this works. So the V vector is grabbing the empirical CDF from the minimum sample. So if you grab all the minimum samples for every row in the matrix that I showed earlier, you can actually call in MATLAB empirical CDF, and I'll give you like a CDF, like a numerical function. Okay, so you can actually stack that up here. And then what this is saying is that somehow the inlier ratio is the scalar that allows me to linearly combine these two to predict this value, right? So then it means that this E, when you multiply by this matrix A, should be able to get me or predict this value, sort of like a regression problem here. So in order to construct this matrix A, what I'm going to do is evaluate the minimums that I got and evaluate the CDF for the good matches, or what I believe is using the model that I just found out, or for the correct matches, and then the model of the GEV for the false correspondences, evaluated at the distances that I have. Then I want to make sure that the sum of these guys, which are the scalars, so that I can have my model as stated, has to sum up to 1. And then this was more like a hack that allows us to actually get better estimates, and I'll explain that in a second. So this is basically just bounds on the solution. Okay, so obviously this inlier ratio has to be larger than 0, but it has to be upper bounded. In theory, this epsilon is 0 and 1, between 0 and 1. But then we found out practically that this tau, which is actually the inlier ratio estimated from the predictor that I introduced earlier, helped us to actually force the algorithm or the solver to get with a good solution. Sorry, here I have a mistake. Should be over epsilon. Let me show you some results with this algorithm. So top row I'm showing for SIFT features, bottom row for surf. So this red plot here is just showing the histogram of the minimum distances coming from the false matches. No, sorry, from the true matches. And then the red curve is the curve that I found out with the proposed algorithm. Then here, the blue one is for the false matches. This is the GEV that I found, the generalized extreme value distribution. And then when I solve everything, this is the curve that I got, the green curve, the continuous curve. And then the histogram is actually the histogram of the minimum distance that I observe by just grabbing the minimum distances from the matrix. Now, this black plot is the weight that I get by just applying the Bayes formula to get the sort of like a confidence on correctness. And well, as you can see here, at least qualitatively, the fit is actually quite good. It's actually not that bad, even though that there are a few hacks to make it work. Now, this gives a good general picture that the algorithm is working. But what about the estimates of the inlier ratio itself? So here I'm showing this table where I have several image pairs, and I have 3 columns. So the column with no squiggle or anything is just the ground truth. So that's the ground truth. Epsilon hat is the estimate that I get by solving the least squares I proposed. And epsilon tilde is a modified least squares, except that I don't have this upper bound with the tau that I was mentioning before. So the observation here is that if I actually don't put that upper bound, the solution tends to overshoot. So for example, consider this row. So if I don't put the upper bound, the value is super wrong. So it overshoots. But when I put the upper bound, it actually behaves a bit better. So you can see the same trend in other image pairs, even with different descriptors. So this actually works.
When you put the upper bound, do you actually reach that upper bound? Is your epsilon hat basically the upper bound that you imposed?
Epsilon.
Equal to tau?
No, it's actually different. It's different from tau.
It's lower than tau?
It's lower than tau. Yes. And yeah, this made it work better than without the upper bound. Okay, so this is just to get the results of the model. Okay, but then this is not showing the speedups that I can achieve with a Runsack approach. So I'm showing this table on homography estimation, and our approach is called EVSAC, which is shown in this column. We're comparing this with Runsack and other methods that are also accelerating Runsack convergence. The most famous one is actually PROSAC. And I sorted the results. So as you can see here in this table, every row is a different image pair. Here is some data. So for example, this first row is using SURF features. Then the second row is SIFT features. And here is the number of correspondences that I got. And then this epsilon is the ground truth for that image pair. So this means that only 1% of the candidate correspondence was correct according to the ground truth. And I sort them. Okay, so the lowest inlier ratio to the highest inlier ratio. So these are too many numbers, but I want you to focus on these boxes that I'm highlighting. So what you can see here, for example, consider the first row. Models means the number of hypotheses that the algorithm had to draw in order to reach to the good solution. And then time here is just milliseconds, the number of milliseconds that it took to actually converge. So what you can see here is that actually EVSAC, thanks to this model, it only took 4.2 milliseconds to actually reach to a solution, compared to, for example, PROSAC, which is actually faster, but the number of good runs means that out of the 300 trials that I got, EVSAC 100% of the time returned the same answer, which was good. But PROSAC only less than 1% return a good solution. Then the remaining results were completely wrong. So this means that EVSAC tends to be more consistent than others. And of course, in this case, Runsack took forever, never converged, and so never returned a good solution. And you see the same trend as you go down. EVSAC is very competitive, especially when the inlier ratio is very low. But when you start getting a higher inlier ratio, meaning that you have more good correspondences, then EVSAC tends to behave on par with the competing methods. Okay, so the real advantage here is when you have an image pair that is not that well behaved in terms of that we don't have that many inliers. Okay, so now that actually comprised the part of what I did or what I tackled as part of my PhD. And then I'm going to talk about some other topics that I'm recently working. And these are actually results that I haven't published yet formally, but I just want to show where I'm going and what I'm thinking in terms of research now. So I'm going to show an approach to learn from a long-tailed data set, and this is work that I did with Deva Ramanan from CMU last summer, although we are still working on it. And the motivation came from this picture, right? He's very excited about the open world problem, and then I got excited about it as well because it deals with rare data. And clearly the problem, if you actually train, say, a network using this data set, very likely the network is going to bias, right? It's going to do very well for the classes that have a lot of samples, but it's going to do poorly for these concepts that only have a few samples. So this problem is actually different from few-shot learning because here we're actually trying to tackle both problems at the same time. So you have concepts that have a lot of samples, but others that only have few. So how do you make the network world behave well for both of them at the same time, right? Now also the community hasn't or doesn't have a good evaluation protocol. So another contribution that we believe is useful is a protocol that we're proposing here. Some previous work that are tackling this can be categorized as follows. So sampling-based solutions essentially say, well, if you have this unbalanced data sets, well, try to balance it. So you can probably undersample some classes and try to come up with a training set that has fairly the same number of training instances. The meta-learning approaches, they're actually very interesting. So what they do in a CNN is that they train another module that predicts the grading updates for the classes that have only a few samples. Okay? And then some other problems that are actually very related, few-shot learning. Well, these are actually fairly recent, but each of them is very different. And then cost-based essentially is imposing penalties in the optimization problem, right? It's going to penalize the classifier if it's actually doing a poor job for classes that are not well represented. So what we're proposing is something very simple. We wanted to come up with something simple because that's what people, adopt more easily, right? So the idea was, yeah.
So in all these examples, you have images and labels. It's
Yes.
just that you don't have a lot of.
Yes, exactly. So yeah, this picture.
There's no unlabeled data.
Yeah, there's no unlabeled. Everything's labeled except that you have, for some more than others. So what we propose is, can we learn an embedding that allows us to deal with this on balance, okay? And the idea came up mainly from a Gaussian mixture model. If you think about every single concept that you want to learn and it is represented from a single Gaussian distribution, then you remember that in the Gaussian mixture model you have these priors that somehow are encoding or can encode the imbalance in the data set, right? So the idea is to have that model to then take that out of the equation and see if the classifier will do better if we somehow tweak it to ignore that imbalance. So the idea of this embedding is actually to represent each concept with a single centroid, and hopefully the network will learn a function that minimizes the interclass variation, so that we can have a compact representation for all the instances per class. So here I'm just giving you an example of how this works. So cats are very popular on the web, cars as well. But when you search for a white reindeer, it's very unlikely that you will find many pictures. So that's the overall idea. And one of the benefits that we thought this could have is the following. Compared to linear classifiers, if you have your linear classifier and you have a new training instance, say for example false in this region, then very likely this new instance is not going to give you an update of your parameters because it's already classified correctly. But when you add another instance using this center-based approach, then very likely that center has to move. Okay, so it is actually very sensitive to that. And we think that this is actually a benefit of our approach. So in order to learn this embedding, we propose this optimization function. So classical cross-entropy loss, where we have the embeddings and W are the parameters of the network. And then we have the centers, one center per class. And then if you only consider this part of the equation, essentially it's just encoding the nearest class mean classifier, okay, which is very similar to the nearest neighbor. It's just going to assign the class to the closest mean. And then we added a regularizer here just to make sure that these centers, which are actually optimized or learn using regular deep learning methods, just so that it complies with the statistics of the embedding as you run your optimization process. So here, this term is just grabbing from the mini batch, or is computing the center from the mini batch, and then enforcing that the estimates are close to the center that is being estimated from the deep learning framework. So this is the objective function that we propose. As you see, it's actually it has some relationship with linear classifier, which makes it easy to implement. And the relationship is the following: if you expand this quadratic term, you will get this, and then essentially you directly establish a relationship with regular softmax classifiers. With the exception, though, is with this bias over here. This bias is actually constrained by these terms. So the bias is actually half of the center of the class that you have in hand. This term actually can be factored out and then cancels out. So the relationship with linear classifier is that essentially we're feeding linear classifiers where the W represents the center, and then the bias is actually restricted by the norm of the center, or the norm of the center. This is useful for implementation details. Now, in terms of the evaluation protocol, what we propose is the following approach. So we have the imbalanced data set. And what we want is actually to capture and see if the classifier generalizes well for classes that are not well represented. So what we propose is to actually sample the training set multiple times, and then for every sample, train a different model. Okay? Now that I have those models, I'm going to use the balance set in order to make sure that the classifier is actually generalizing given this different samples, right? This is just to measure and see if I have a class variation for some concepts, can this generalize? And then normally you just plot or report the per class accuracy average. So out of those trials that you had, report just the average for those trials for every class, right? That's what we propose in comparison with other methods, which are just train and then evaluate using as if you had a balanced data set, which may not be right. So here are some results. On small scale data sets, I compare this with other center-based approaches. One that was recently published at CVPR 2017 was iCarl. Essentially, iCarl grabs a softmax, computes all the features for all the classes that you have, and then computes the center for every class, and that's it. So there are two versions. One that is unnormalized, which is what I just described, and then normalized means that all the vectors that you are dealing with, they have to be normalized. And the reason that they used it, according to them, is that actually helps reduce some noise effects in the data. Then I just use the regular GMM approach. After I have the softmax representation, I fit a GMM, and that's it. Those are the baselines. So on the right, you will see the accuracy, the average of the softmax classifier. And as you can see here, for example, for MNIST, you know that MNIST is actually a balanced data set. I actually had to long-tail them to make that imbalance. So as the index grows, the imbalance grows here in the plot. So as you can see here, the average or the accuracy drops when that imbalance occurs. This shaded region is just the standard deviation that I got from the trials. Now, the plot on the left is just showing the relative performance. That means the accuracy that I got from every of these methods divided by the accuracy that I got from the softmax classifier. This is just to clearly see if there's an improvement or not. Clearly, if there's an improvement, you get something larger than 1. If there's a drop, you will see points below this line. So in the MNIST case, most of them actually behave okay, and that's because this data set it's not that complex. But once you actually analyze other data sets, for example, Cypher 10, you will see that actually the center-based approaches especially improve the accuracy on those classes that are imbalanced. Okay? Well, you can see that actually the problem is hard. So softmax tends to bias a lot for classes in the head, meaning those that are very well represented, but it does very poorly with classes that are not very well represented. Now, when we increase the scale of the data sets, it's a little bit harder to note the improvement here, though, but there is some improvement. So here, if you look closely, the black dots are actually above the line, which means that we're actually observing an improvement thanks to this center-based approach. And same here with another data set that is called Tiny ImageNet. So this is the proposed approach, and you will see some dots that are above the line. So which means that this approach is somewhat helping. And just to clearly emphasize what's going on here, I summarized the relative performance for classes in the head and classes in the tail for different methods. Here I didn't consider the Gaussian mixture model because actually, as you saw, it's not performing well. And for all the data sets that I consider. So for the head, the proposed approach is actually showing some drop in performance, but it's actually not that much. So it's very close to softmax. But when you look at the classes in the tail, you can see that number is actually larger than 1, which means that there's, on average, some improvement in terms of classification. All right. So this is one of the current projects that I'm still working on. And then I also want to talk about another project that is visualizing a few things from CNNs that are used for pixel-level tasks. This is also work done with Chunhoon Liu, Ayush Bansal, and Deva Ramanan. And let me give you the motivation of why I wanted to do this. So we humans actually can learn very easily from even a single example, right? But we also have the ability to say, hey, that object I've never seen before, right? So we have that ability of discovering new things and then learn new things by just experiencing the world. That's something that I would like to enable in computing. So some idea that I got was, well, maybe I can actually discover that new knowledge, assuming that that new knowledge somehow looks like an outlier of the already known knowledge, okay? And I already have theory, as I showed earlier, using the feature matching problem. But the problem there is that the theory that I showed earlier was using the nearest neighbor classifier, and then CNNs are somewhat different, right? So somehow I have to establish this link of the nearest neighbor classifier and CNNs. So that's what motivated to study this problem here. And so we introduced something that is called the compositional nearest neighbors approach to visualize what's going on here. So I assume everybody's familiar with pix-to-pix and maybe results of SegNet. So on the first row, I'm showing labeled 2 images, where the idea is that you pass the labels of a facade in this case, and then the CNN will generate an image that agrees with this input. The compositional nearest neighbor is actually something that is very simple. So if you grab your trained CNN, and then you grab the last layer of your convolutional neural net, and then you grab a specific patch corresponding to 1 pixel and use that as a feature descriptor, then you can actually search for the nearest training patches in your training set and then create this image that looks a lot like what the CNN is actually generating. Even though it's noisy, that may be because of the parameters that we used, but somehow we are able to replicate the results of the CNN. So this is using pix-to-pix. This is using another CNN, which is SegNet. And as you can see here, if you just compare these two, they overall tend to have similar behavior, even though there are some artifacts there. Now, this column, it is classical nearest neighbor, where you will represent the entire image using some bottleneck feature of your architecture, and then just retrieve the most similar image from your training set. So just to be clear, say that I want to synthesize the value of this pixel. What I will do is grab a patch from the last layer of the CNN, use it as a feature descriptor, and then search in my training set. So in this case, I'm visualizing that I found that maybe this is a window that looks like this. And then what the compositional nearest neighbor is doing is just grabbing the information from the training pair, grabbing the RGB value here, and copying it here. Okay? What is nice about this approach is that this allows us to get correspondence, meaning that I know why this value is maybe brown, and that is because it's coming from this training set that is very similar to in appearance at least.
So you do this per pixel?
Yes, this is.
You don't average the patches with overlap?
Yeah, not at this time, but that's one of the steps that we're considering. So right now it was sort of like a proof of concept of seeing if this is actually working or not. And somehow it's actually replicating the results. For example, something that caught our attention was, why is it that the CNN is drawing this red, I don't know what that is, but this red region? Well, we found out that it's actually coming from this image that has that. So somehow it's actually replicating that. And so we came to the conclusion that maybe it's memorizing the training set somehow, and then it does some sort of a fast nearest neighbor synthesis, which is similar to what we're proposing here. These are more results on the same idea. datasets are facade, cityscape, and Canvid. So these are results for pix-to-pix. These are for SegNet. And so as you can see here, pix-to-pix and the compositional nearest neighbors, they actually tend to look very similar to each other. Okay, same here for SegNet. And so it looks like, it looks like the networks are memorizing somehow the data set and then replicating that information. And some interesting feature as well is that patch that we're using as a pixel representation, we know for sure that actually encodes sort of global information but also local information. By global information, I mean, for example, the color of the facade. And for the local information, for what kind of window style are we rendering? So somehow the network is able to figure that out and embed that information there. More results on other data sets, from labels to images, and then from images to Google Maps like images. So as you can see here, we replicate a very, very similar result. Now, another interesting observation that we saw here is that what if instead of rendering the expected output given by the pairs, right, because it's image translation, can we reconstruct the input image using the same approach? And it actually turned out to be good as well. So if we use the same representation but reconstruct the input from the training set, we can actually do so. So for example, consider this row over here. We were able to input this image, which has never seen before by the CNN. And then by doing this compositional nearest neighbors, we can actually reconstruct it. It actually resembles the scene very well. So this is something that got our attention. And it looks like the representation is so good that is even encoding things from the input that is allowing us basically to just find the information from the training set and then just copy and pasting the information as the final output. So this happens also with other type of data like labels.
So here you don't have any smoothness constraint or homography or anything?
Yeah, nothing like that.
How do you make sure the patches are coming from the same image? Like, why isn't it all different colors or different?
Yeah, that's what I'm saying here before. That somehow the network learns that, so it contains this global information exactly of what color of the facade we're rendering, what kind of style of facade. But but also local information, the windows information, for example, what kind of window is it? Is there a glass there? So these are intriguing results that we're still working on this. But yeah. Now, the last experiment. If you're familiar with pix-to-pix, they're using a unit architecture. And it has this bottleneck, and then you have a lot of decoding layers. So it looks like that the network is actually using the bottleneck to retrieve similar images and probably use the most similar one as the basis. And then as you progress over the deconvolutional layers, someone is morphing the output by adding more details and details and details until you reach to a final output. So for example, this peak that you observe here, which is the output of the convolutional layer, it can be explained that it came from the most similar image. Okay, so it looks like the CNN is just morphing, for every deconvolution that you're actually doing until you reach the final output. So we're still working on this. We have more experiments, and one of the next steps.
So
yeah.
I can understand these deconvolutions, but bottleneck, how do you compute the bottleneck?
When you do the forward pass,
Yeah.
you will get deactivation of the bottleneck and use that as a whole descriptor of the entire. Yes, exactly. It looks like it's grabbing the most similar image.
As you go through the convolutions here, you're also grabbing
Patches.
smaller and smaller
Exactly,
patches, right?
exactly. Yes, yes. That's exactly right. All right, so that is actually pretty much it. So just to give you some conclusions of what I presented today. So I hope I convinced you that extreme value theory is actually it's a good theory to model rare data. I showed that with feature matching. It allows us to predict good correspondences and also speed up Runsack estimation. In terms of long-tailed data sets, it looks like center-based approaches are I mean, it's giving some insight that we may be up to something there, but we still need to work on that more. And then this visualization framework to understand pixel level tasks from CNNs are still intriguing, right? And so now with all these unseen inputs to the network, we can explain how it'll behave, at least using this framework that I introduced. All right, so that actually concludes my talk. If you are more interested about some other projects that I have in AR or structure from motion, feel free to stop by my website, vfragoso.com. And yeah, that's pretty much it. Thank you.
So this last set of results you had, the network was trained on segmentation data?
Yeah. Yeah, so
So those are the sort of outputs.
Yeah.
Right?
Yeah.
And then, but when you look at the results, it seems like you can reconstruct the input image, right?
Yes.
Fully. So what happens if you give it random segmentation data? If the segmentation data is not correct, if it's just random image every time?
We haven't tried that.
You still get the same behavior.
I don't know. I wouldn't be able to answer that, but I assume that it'll do the best to actually replicate the results based on this. Yes. Yes.
So the labels don't really matter.
It looks like it's not. I'm not sure. I take it with a grain of salt. I'm not sure. I'm not sure what will happen. That's what I'm saying. We're still working on this. I don't want to give a bad answer now. But yeah, it's very interesting, I believe.
Questions here? No, I believe none of you will have one-on-ones, so hopefully more discussions will follow. Yeah, let's send the speaker.
Thank you.